Hey all, this is Kaustav here. Today I'm presenting my peer graded assignment for the course Machine Learning Foundation for Project Managers. In the beginning phase of this project, I set out to apply the complete machine learning methodology process using a real world dataset. The dataset is a combined cycle power plant hourly reading to predict the electrical energy output. The aim was not just to build a predictive model, was to understand the key steps behind it using the Microsoft without writing any code. This project is framed as a practical exercise to apply everything that I have learned, identifying the relevant feature, choosing the right type of modeling approach, and evaluating the model based on appropriate metrics. Since PE is a and when we go further, we'll see various variables, out of which P is one of the target variable, and P is a continuous variable. It makes a regression problem. This means we are not classifying the output into categories, we are just predicting the numerical value. That is why I choose a linear regression approach using the Excel's built-in analysis toolpack. Okay, now we go to the raw data. If you see, in this particular tab, I began by importing the complete data sets provided by the codes, right, which is combined cycle power plant project. The dataset includes 9,568 hourly average reading for the power plant sensors. Each row represents 1 hour of operational data and variables collected. The variables that are collected are temperature, exhaust vacuum, represented by V, temperature is represented by T, and ambient pressure, that is AP, relative humidity, that is RH, and PE, which is the electrical energy output, which is a target here. And before doing anything, I ensure that the data types are consistent. There were no missing entries, and the variables made intuitive senses. So correct. So after that, what I did, we use randomize to divide the data into three different set. One is a training set, validation set, and a test set. So what we did, we use randomize. So please split the data set into three part. As I said, training set, which is 65%, validation set, which is 15%, and test set, which is 20%. The idea behind this is to mimic the real modeling process, where we don't evaluate our model on the same data we trained it on. So, and randomization helps ensure that the split is not biased and by any way. The first portion, there is a 65%, that is a training data we use to train the model to see the fitment of the parameters, right? Validation we use to tune the model and choose the correct model, which you will be seeing in the upcoming discussions. And the test is the only we will use only once we have evaluated the correct model, and we use that correct model to evaluate this test model. Now I will be going to the first training model. If you see the training model, I have all the training data available here, and I have used Excel formulas to predict the predictive P and residual value, all this. Now in this phase of the project, I ran a linear regression model using only the training set, which includes four input feature: temperature, exhaust vacuum, ambient pressure, and relative humidity. The goal here was to understand how well these variables can explain the energy output of the power plant. From the regression summary, the first thing I looked was the R square value, which indicated how well the input variable explains the variation P. A high R square also shows a good model fit. So if you see, and the R square value, it tells us approximately 92.94% of the variability in the target variable, that is PE, is explained by the selected input features. This indicates a strong model fit. At the same time, if you see the adjusted R square, it checks if the number of features used are appropriate. Standard error and the significance of F are also inspected to confirm that the model has a statistical relevance. So if you see the F and significance of F, these values confirm that the ANOVA table comes from the ANOVA table and tests the overall significance of the model. The extremely low significance of F means that the model is statistically significant, and the input features collectively explain the meaningful variation in the output variable. Now we go to the validation set. So in validation set, after training the model, I applied the coefficient for model 1. So coefficient for model 1 are this are the coefficient that we have for model 1. All these coefficient are in model 1, and this is the intercept. So after training the model, I applied the coefficient for model 1 to validate the validation set and calculate the performance metrics. So performance metrics, what we mean here are the MAE, that is mean absolute error, the mean squared error, and the mean absolute percentage error. We have calculated similar metrics for our training set also. So when we go into the training set, we have similar mean average, mean absolute error, mean squared error, and mean absolute percentage error. These are also calculated for the training set also. Okay, now this metrics, whatever we calculated both on the training and the validation, helps us to evaluate how far our model predictions are from the actual value. So the validation matrix gives us an insight into how the model might behave on unseen data. When I say unseen data, that is the test that I am talking about here. And it also helps us identify if there's an overfitting. So for model 1, the variation results are reasonably close to the training performance, which is promising actually. So if you see the average residual value, both the values are very close to 0. But the average residual would be whatever residual, that is the difference between the actual PE, actual prediction, and the predicted PE. So we take average of that, and average for both the values are very close to 0. So model shows no strong over or under bias. If you go to the squared mean squared error, only a marginally high. So when I pulled the training data values and the validation set values for my output metrics, which is mean squared error and mean absolute error, so only there is a marginal difference, and which indicates a consistent prediction accuracy. And for the absolute mean absolute error, they are very close. The 3.6 and 3.74 model performs similarly on unseen data, and the mean absolute error is only 2% increase, confirms the model generalizes well on the new data. Now one of the requirement was to see if all the there is a requirement for a new model, or if this model is fit or not. So what we did in new model, so we are exploring if the model can be simplified. So in the first model, all the four features, that is AT, V, AR, and RH, are all included. From the regression output, we see that all the features are statistically significant. So when we talk about statistical significance, we talk about the value of p, right? So value of p for all of these cases are less than 0.05. So when you see these numbers, we have e, and the scientific numbers are actually less than 0.05. However, if you see the coefficient of um, the ambient pressure, that AP has the smallest coefficient, so and contributes the least in the magnitude. To simplify the model, we could try to remove AP and compare the adjusted R square and the error matrix. If the performance does not drop, no, we can justify that only three features are good enough. So the primary reason of we coming up with a new model, or testing a new model, is to see that if we remove ambient pressure, which is only 0.068, the coefficient is, which is very less in compared to if we see the other coefficient. It doesn't matter if the other coefficient are negative or positive, but the exact absolute value is very less. Then how the new model will perform. All right, so what we did, we created another training set, wherein we removed the feature ambient pressure. AP is no more there, and we calculated all our data analysis based on the only this three feature and PE as our target. Then using the same training set, I ran another linear regression. The time this time, obviously I excluded the AP as I highlighted. The key observation here was that the new adjusted R square, so here is a new adjusted R square, remained almost same as in model 1, which suggests that removing AP does not reduce the model performance. Additionally, the standard error was comparable. So so what I did a model comparison here. If you see, as adjusted R square, as I was talking about, was almost the same. It's 0.96 and 0.96 same. So which means that the AP does not removing AP does not reduce the model performance. As well as if we see the other output metrics such as MAE, MAC and MAPE, so lowest is the better. So the new model, and we have calculated the training set, we have also done the validation. Okay, and we took details from all the data that we took uh, tells me that model 2 in model 2 all this output matrices are lower, and lower is the better. So that makes a smaller average prediction error. This also mean squared error also penalizes larger error but less severity. So even though it penalizes larger error, the severity is less. So this model 2 without AP ambient pressure performs better in the all output matrices while maintaining clearly the same adjusted R square, which is also simple and using only three variables, and which reduces the model capacity and potential noise. So that brings us and this helps us decide that we should be using model 2. So what we do in a test set, and test set is, again, there's a segregated already we have done earlier. uh, the model the final model evaluation is done on the test set, which has not been used in all of this training and validation. I applied the model 2's coefficient. So model 2's coefficient is something that we got here. Model 2's coefficient we used, and again calculated the MAE, MAC and MAPE, and the test set matrix closely matches with the validation matrix, which confirms that the model 2 generalizes well completely new data. This reinforced our confidence in the model's reliability and the process used to build it. But so model 2, as we see, is the correct more simple one. So we use that, and that gives us a better result. So if you see the final test set, if you take the test set and the validation set, there is a slight improvement. um, so MSC technically mean squared error has come down. So coming down is, as we know, lower is better, and mean average percentage error has also come down to 79%, so which is better relative prediction accuracy. We have a slight changes in um, the mean average error, but which is practically the reason of the data set that we're choosing. But our two main output metrics gives us tells me that model 2 is a better representative model. Thanks for your time, and now I conclude my project.